Hello learners, my colleague has tackled the definition of enthalpies. He has taken you through the endothermic and exothermic reaction, even gone to the extent of describing how you use a thermochemical equation in calculating enthalpies. I will go on to calculate enthalpies of reactions. That is going to be our main focus in this particular session. There are three ways in which you can calculate enthalpies. You can get enthalpies using Bode energies. You can also calculate enthalpies from experimental data, or what can sometimes be referred to as empirical data. You can also calculate enthalpies by use of what is referred to as the Hess law, or the law of constant heat summation. Now, in this particular session, I will tackle the calculation of enthalpies using Bode energies. Now, the first question that we need to ask ourselves, a very simple question at that, what is a Bode? What is a Bode? What is a Bode? Now, in our day-to-day life, we know a Bode is that which ties substances together. We are in chemistry, however. So, we shall be interested in that which hold chemical substances, atoms, ions, molecules, that which hold all the force of attraction between those particular particles, the ions, the atoms, and the molecules. How are they joined together to form chemical substances? Now, having said that, from our Form 2 work, we know that we have three types of Bode: ionic Bodes, covalent Bode, and metallic Bode. We want to calculate enthalpies from Bode energies, but please note, when I talk about Bode energies, as far as thermochemistry is concerned, it has nothing to do with ionic Bode. Actually, when we get to ionic Bode, we shall define some term that we shall call lattice energy. Lattice energy, that is the energy involved in ionic bonding. So more details shall come to us later on the same. For metallic Bode again, we shall come up with the term that we shall call atomization. Atomization or sublimation energy. That is as far as thermochemistry is concerned, the bonding, the energies involved in metallic Bode shall be called atomization. The energies involved in ionic energy shall be called lattice energy. So specifically, we are interested in covalent Bodes. Covalent Bode. So we define a Bode energy. My colleague has just said that there is a quantitative aspect in every definition. So Bode energy becomes the energy required to break a mole of covalent Bode and other standard states. That needs to be noted. The quantity is a mole. And again, this time we are talking about covalent Bode, the energy that is required to break a mole of covalent Bode. So we want to proceed to calculate the enthalpies of reaction from Bode energies. This is what you need to note, that a chemical reaction shall invariantly involve two steps. It shall involve Bode breaking and Bode formation. Any chemical reaction shall involve Bode breaking and Bode formation. I think we must have come across that sometimes in the course of the study of chemistry. Like it was said that nitrogen is rather unreactive. Why? Because a lot of energy is required to break the Bode. So how does that tell you? That before you react nitrogen, you must break the nitrogen into nitrogen atoms. From the nitrogen molecule, you must separate it to nitrogen atoms. So those are the two processes that are involved in a chemical reaction: Bode breaking and Bode formation. Now, we need to note that Bode breaking is an endothermic process. An endothermic reaction has been defined in a previous part of this topic. Now, again, Bode formation is an exothermic reaction. It's an exothermic process. So at the end of the day, whether you are going to get energy or energy is going to be required, it will depend on the relative quantities of the two. Are you using more energy than you are getting, or are you getting more energy than you are using? And we can look at that in terms of an energy level diagram. Now we have drawn some two energy levels, level diagrams. In the first one, I am using all this energy. I'm using all this energy to break the boards. But after that, I'm getting this amount of energy. So you realize that the amount of energy that is being used to break boards is more than the energy that is being used to form boards. Therefore, at the end of the day, it is going to be an endothermic process. Energy is going to have to be absorbed from the surrounding. When you look at the other, it's a reverse of the of this one. You are getting so much, you're using less amount of energy than you are producing. So it becomes an exothermic reaction. It becomes an exothermic process. Now, having said that, let's deal with an example. And the question is, calculate the enthalpy of combustion of methanol given the following board energies. And the board energies are as given there. Yeah, they are last given there. Now, there will be a few steps that shall be adopted that we shall take to determine the enthalpy of combustion of ethanol. Now, the step number one, of course, is to write the equation. We want to write the equation of that reaction, and the reaction is right there. But the way this reaction look like, remember, I have to separate the atoms. I have to get some carbon that will be reacted with some hydrogen, reacted with some oxygen. So I have to break a number of bonds. At the same time, I'll have to form some other bond. So to make that simple, I will represent this same equation but use structural formula. The structural formula that we studied in Form 1 or 3, or in Form 3 in organic chemistry. I've just split the methanol. I've written the oxygen the way it is. Note that this is what was taught in structure and bonding, Form 2 structure and bonding. The bond in oxygen is an oxygen to oxygen double bond, and similarly to the carbon 4 oxide, 2 carbon to oxygen double. So I've just rewritten that equation, but the structural way, the way the atoms are actually arranged in space. So my first assignment will be to determine the bonds that are broken. Now, looking at this structure, I have to free the hydrogen. So I have to break some carbon to hydrogen bonds. And I think I have 1, 2, 3 carbon to hydrogen bonds. But now I have two molecules of methanol. I have 2 molecules of methanol, each of which has 3 carbon to hydrogen bonds. So I have a total of 6 carbon to hydrogen bonds. And according to the data I was given, each carbon to hydrogen bonds requires 413 kilojoules. So a total of that much, 2,478 kilojoules, will be required to free all the carbon and or to break all the carbon to hydrogen bonds. Now next, I have to break this particular bond, the carbon to oxygen bond. Note this is a CIGO bond. This is a CIGO bond. Now I have only 1 per molecule of methanol, but I have 2 ethanol molecules. So that gives me 2 carbon to oxygen bond. 2 carbon to, then I go on to break the oxygen to hydrogen bond, and there are 2 of them because of that, and all that energy will be required. Note, I also have to break the oxygen to oxygen bond. Then I get the total amount of energy that is required for bond breaking, and that is giving me 5,607 kilojoules. Note that that is energy required because, as we have just said, bond breaking is endothermic. Then I move on to the bond formation. I have 2 molecules of carbon 4 oxide, right? Each molecule has 2 carbon to oxygen double bond. Yeah, these are double bonds. I have two. Note that a double bond is not the same as two single bonds. I think that needs to be noted. Yeah, so I have two carbon to oxygen double bond, but I have two molecules of carbon 4 oxide. That gives me a total of 4 carbon to oxygen bond, and that is the total amount of energy that will be produced by the formation of that bond. Then I get to the water molecule. We could hide that for now. Each water molecule has 1, 2 OH bonds, but I have 4 water molecules. That gives me a total of 8 HO or OH bonds. A total of that amount of energy shall be produced by the formation of that. So in total I have 6,932 kilojoules produced. Now let's skip that for now. Get to this diagram. I want to represent that in an energy level diagram. So for the energy that is required to break bonds, it is coming to 5,607. That is the bond breaking. Then the total amount of energy is produced when the bonds are formed is that much. So you realize that I'm getting more than I used. So the process becomes exothermic. The process is exothermic. So you can as well just subtract them and put a negative sign. Alternatively, you could add them up, but remember, bond formation is exothermic. So I have a negative there, and bond formation is endothermic. So I can just add the two, but remembering this, remembering that. Now, some students ask me. In the previous, my colleague has talked about a reaction. The delta H of reaction is equal to H P minus HR. Why is it that we don't use this expression? Why can this expression be used at that particular point? So note, we don't even in this particular, we don't have the heat of the product. We don't have it. If we had this, we don't have this value. We don't know exactly what this value is. That is why we cannot use this. We don't know what this value is. What we have are the changes. The changes when you break bond and when you form the bond. So you cannot use these to determine the enthalpy from bond energy. So now remember, the question required us to get the enthalpy of combustion of ethanol, but what you have from the equation is 2 moles of ethanol. So the other step is simple. Just divide that by 2 so that you can get the amount of energy per mole of methanol. Per mole of methanol. Just divided that by 2. So I got 662.5 kilojoules per mole. Note unit and the sign, and remind yourself how to write a lowercase k. Yeah, what makes k lowercase is that tail. Without that, your units are wrong. Your units are as well not there if they are wrong. If they are wrong, you will still be penalized. If you don't put that negative, you don't put the correct unit, you lose half a mark for that. Now, having said that, I hope it is understood, and I wish that you could handle this particular question. You calculate the enthalpy of combustion of hydrogen given the following bond energies. At the end of the day, that should be the answer. Confirm that that's what you get from that calculation. It will be fun getting to that particular answer. Now, so my colleague has talked about the enthalpy of solution, and now I add, or I continue with the enthalpy of neutralization. First, what is enthalpy of neutralization? Now, enthalpy of neutralization is the amount of energy produced. Yeah, I expect neutralization to be always exothermic. When an acid reacts with a base to form 1 mole of water, that becomes the key to the definition, the quantitative aspect. You must react enough acid with enough base to form 1 mole of water. 1 mole of water, therefore, is a denominator, common denominator for all neutralization reaction. Therefore, the enthalpy of the reaction of neutralization shall be the enthalpy of that particular reaction. I need to note that for all strong acid, strong base pair, enthalpy of neutralization is going to be constant. Now, what do you mean by a strong acid? One that undergoes complete ionization. Strong base, one that undergoes complete ionization to form hydroxide ion. The acid should of course form hydrogen. And that is understandable because at the end of the day, the sulfate, the nitrate, the chloride will be spectators. The sodium, the potassium, they will just be spectators. The only species that are taking part in the reaction are the hydrogen and the hydroxide. The rest are just spectators. So for all strong acid, strong base pair, the enthalpy of neutralization is 57.4. The equation, the reaction involved is constant for all of them. However, if any of them is weak, you have weak acid like methanoic acid, carbonic acid, or like we are talking about mostly the organic acid. The enthalpy of neutralization is going to be lower. It's going to be the energy of neutralization for when one of them, both are weak, is lower than 57.4. Why is that so? Now note, at the end of the day, you must get 1 mole of water. For you to call that the enthalpy of neutralization, you must get 1 mole of water. However, when you talk about a weak acid, we don't have 1 mole of hydrogen ions in that solution. Yet you have to get 1 mole of water. So to free the hydrogen ions, you need to ionize the acid. You need to ionize the acid. Some energy is going to be required to ionize the acid. So not all the energy. So the hydrogen ions available will react to form water. But instead of this energy being given off to the surrounding, it is going to have to go back to the system to break the bonds to produce more hydrogen ions, to produce more hydrogen. So energy is required to ionize the base or the acid. So the enthalpy of neutralization is going to be lower. Now let's deal with an example. Having said that, let's deal with an example to determine the enthalpy of neutralization. And I want to look at some form of an experimental approach to the same. Now what do I have? I take 25 cubic centimeters of sodium hydroxide. It's given as it is 0.8 molar sodium hydroxide. I take 25 cubic centimeters and probably put it in a plastic beaker. We've been told that it's going to. Then I measure a temperature, and definitely it's going to be around room temperature at 23 degrees Celsius. Then I add some nitric acid in 5 cubic centimeters portions. 5 cubic centimeters portion. When I add a 5 cubic centimeters, I measure the temperature. So you realize there is an exothermic reaction. Energy is going to be produced to the surrounding. The temperature will rise to around that. Then I add some more 10 cubic centimeters. The temperature continues to rise. But then after some time, after maybe I've added some 15 around there, you realize that I've added some 5 cubic centimeters, but instead of the temperature rising, the temperature has dropped. What must have happened here? Definitely, the reaction must be over. I am continuing to add some cold nitric acid, yet there is no more reaction. So the temperature starts to drop. The temperature starts to drop, and I can do that up to the 25. Now, what I want to do is to determine the maximum temperature attained and to know exactly what volume was required to react with the 25 cubic centimeters of sodium hydroxide. Now, what do I do? How do I do that? I need to draw a graph. And that is exactly what I'll do. I sketch a graph. I have a sketch here, but this is what you need to note when you draw a graph. Graphs normally carry some 3 marks. They normally carry some 3 marks. You will get a mark for labeling your axis. Just draw a line. Just draw a line, put an arrow. If you, put an arrow. That's what you were taught in baby class or somewhere. Then label the axis, maximum temperature attained. Then draw another line, label the volume of nitric acid, and please put the correct units. So that will earn you half a mark. Now next, there will be a mark for the scale. What about the scale? Your size, the size of a graph, the size of your graph. And when you talk about the size of the graph, we are talking about the area occupied by the plot. This is my last plot, and this is my first plot. How many boxes? 1, 2, 3, 4, 5, 6. 6 boxes out of the 8. That is more than half, or more than 3/4, as the case may apply. So the size of the graph, it must cover at least 3/4 of your paper. The consistency of your scale, the consistency of your scale, 23, 24, 23, 24, 25. The consistency. Now, what becomes very critical is like when you write a big 0 here. When you write a big 0 there, then you get 24 here. The consistency is no longer there. You don't longer have a scale, because from 0 to 24, you have 24. But from 24 to 25, you have only one. You are only allowed, therefore, to plot values in the first scale, the first correct scale. If any other plot will be wrong, because your scale is not consistent. If the scale changes, we only look at the first scale, not any other. So the consistency of the scale. Now finally, is your scale accommodative? Does your scale accommodate all the values? Now you find some students, they have plotted up to here, but it doesn't fit. Then they get a ruler and then they draw some lines. You've lost a scale mark, my friend. That scale is gone. So you must ensure that your scale, all your values fit in the graph, whether you draw them or not. If I look at the table and I see there are values you've not drawn, you lose the scale mark. Then you need to plot. Please use crosses or dots, whichever but let the plots be visible even after you have drawn your line. Then most importantly, the line. Thermochemical graphs are straight line graphs. When you look at this point, they look like a very smooth curve. But we don't draw curves in thermochemistry. In energy changes, we draw straight lines with extrapolation. What is to extrapolate? A line is said to be extrapolated if it does not meet at a plot. If the lines do not meet at a plot, then they are extrapolated. Then they should meet above the highest. Those are the only two things that you need to consider. That the lines meet above the highest and they are not meeting at a plot. As you've said, have you seen? This is now my thermochemical graphs, and this is the maximum temperature that is reached, and this is the volume that is required to neutralize the 25 cubic centimeters of sodium hydroxide. Now note that I have shown, it is important to show, maybe for your own ease of reading. There is something called parallax. You want to read and then you close your eyes a bit and you get lost. So if you want to avoid that, just get a ruler and show. Furthermore, you earn half a mark for showing, even if the reading is wrong. Yes. So it's always advantageous to show. So we read this value. I think it's around 29.2 or some value. If I had a good, then this is around 12.5. So what does that mean? When I react 25 cubic centimeters of the sodium hydroxide, it needs 12.5 cubic centimeters of nitric acid, and the maximum temperature attained will be 29.2 at neutralization point. That is a neutralization point. At that point, that value and those will be very critical values for my working. Now, so the questions I'll get from that: determine from your graph the maximum change in temperature. So change in temperature. So 29.3 minus 23 is 6.5. The change in temperature in Kelvin is the same as the change in temperature in degrees Celsius, as my colleague has just said. Then the volume required to neutralize sodium hydroxide, we've just seen from the graph, is the volume corresponding to the maximum. That is 12.5 cubic centimeters. So calculate the molar enthalpy of neutralization of sodium hydroxide. How do I go about that? Now, get the amount of it that is absorbed by the solution using the expression MC delta T. Note that the M value this time is the total volume at neutralization. The total volume at neutralization, the 12.5 plus 25. Definitely, in any one question, you have multiple values. I've seen some students who go on the table and they use 25 plus 25. My friend, you did not use 25 to neutralize the sodium hydroxide. The neutralization actually apparently took place at this particular point. So you need the volumes at neutralization and not the total volume. So so that is important. You need to note that. So you add this volume to the 25 that you had used. So that gives me that amount of energy, 10.23.75 joules. Note the C was given in joules per gram per Kelvin, which said is also equivalent to the degree Celsius. So that and that cancel. So whatever answer you get here will be in joules, capital J for that matter. So, but how many moles of sodium hydroxide did I use? I was told it was 0.8 molar, and I used 25. Remember, in that conical flask, the beaker, I had 25 cubic centimeters. That's what I was adding in 5 cubic centimeters portions. So the moles used are that much, and this should come to 0.02 moles. So the 0.02 moles is producing 10.2375 joules, what about 1 mole? And that is what I have. I've divided by 1,000 to convert that to kilojoules. Please note, it is exothermic. There is a rise in temperature. The temperature of the surrounding is increasing. Then the unit kilojoules per mole. And that is it. Now you could have a look at the other example. This is another approach, another experimental approach, where we take a given volume, 20 cubic centimeters of 1.38 molar sodium hydroxide. You maybe put it in a beaker. Then you measure its temperature. Like I've measured the temperature of that solution every 30 seconds. Initially, every 30 seconds for 1.5 minutes. Then proceed to add 25 cubic centimeters of sulfuric acid to the same. Then measure the temperature from that continuously for